Lesson 6.5, similar figures, page number 475. What we're going to do is we're going to take the proportions that we were working on in 6.4 and the ratios from 6.3, putting those together and starting to compare some things. One of the things that I want to look at is similarity between objects, and this is more of a geometry kind of a area. One of the definitions for similarity of objects is if they look the same and the ratio between all of the sides are the same, then it would be considered similar or proportionate. So if we've got a triangle that's a different size, so let's say that that's 5, this is 4, and this is 3. If I have another triangle, in fact, let me draw that triangle bigger. And let's say that this is 10, this is 6, and this is 8. Now these two triangles would be similar if the ratio of common sides is the same all the way around. So for example, the hypotenuse, or the longest part of this triangle, is 5 and 10. So the ratio of the hypotenuse is 5 to 10, which reduces to 1/2. Now if these two triangles are similar, the ratio of all the other sides that are related to each other will also be 1/2. So this 3 and this 6, they're pretty much, vertical. They look close to the same, so we're going to put those as 3 to 6. That also equals 1/2, which leaves me with my 4 and 8, which is 1/2. So because my ratios are the same, then these three triangles are going to be similar. And what is nice about that is sometimes we aren't given all of this information. Maybe I'm only given this information right here. And I'm told that these two triangles are proportional, but maybe I want to find out the length of that and I don't have it. Well, if I know that the ratios are the same, if I know that my 5 is to 10 or my 5 to 10, that ratio is going to be the same as my 4 over x. All I do is cross multiply, and I get, oops, I'm having a hard time multiplying today. This is 40, and I get 8 for this here, because my ratio 4 to 8 is 1/2, just like my ratio 5 to 10 is 1/2. So that helps out when you're looking at some unknowns. Like for example, if I have a building, and let's make it a little bit taller building, and the sun is shining, and here's my lame sun here, and this building casts a shadow. Okay, probably should use black to show my shadow here. Okay, cast a shadow, and let's say that that shadow is 105 feet. I can take a tape measure out and measure from the base of the building to 105 feet. Okay? And let's say that I also have a flagpole. And it also casts a shadow. But I do know something about this flagpole. I know the flagpole is 21 feet high. Okay? And I also can measure this flagpole shadow. And when I measure the flagpole shadow, I get 15. Okay? So according to my similar figures, because same sun is shining on that shadow is shining, or shining on this flagpole is shining on this building, these are going to be similar. In fact, I could even draw a line here and get a triangle, and a line here and get a triangle, and these two triangles are similar, which means their ratios from here to here is the same as from here to here. Now let's say I'm trying to figure out how tall this building is based on that information. 21-foot flagpole, 15-foot shadow, 105-foot shadow. I'm looking for the height of that building. Well, I can use ratios. Well, this is related to this, x over 21. And my shadows are related. So I started with an X on top. This left-hand building, I'm going to do my left-hand shadow over my right-hand shadow. And I can multiply this through and get 15x equals 21 times 105, which in this case is going to be 2205. Divide by my x, or by 15. Divide by my 15, and I find out then that x is 147 feet. That means my building is 147 feet high. So that's one of the things that's nice about similarities. You don't have to actually measure this height. You can measure the shadows and know the height of a similar object. In fact, some people, what they'll do is they'll take the measurement of the shadow here. Instead of measuring the height of a flagpole, they'll take the height of a yardstick, which is 3 feet. Or something else that's even shorter, and do the same thing and end up with the same answer. Because as long as your shadow is proportional to your other shadow, meaning you took the measurement at the same time before the sun moved, you're going to get similar triangles to be able to figure out what the height of that building is. So even using a yardstick would have worked fine. Well, let's go to a couple of examples on page 479, and let's look at number 8. Doesn't matter what size the object is or what shape it is, if they're told they're similar, you're going to be able to figure out the unknown side. So, we're going to take 48 left over x equals 54 over 36, and you're going to cross multiply, find out what x is, and that's how big that one will be right there. Okay, you can do the same thing on 10. 42 over 28 equals 30 over y. So it's all done the same way there. We're going to skip 11 to 18, and I'll have you do some of the applications on page 481. And what we've got there, we're comparing all kinds of stuff from video resolution to heights of buildings. If you look at 26, one very similar to the one we just did. Same with number 25, but instead of looking at the shadow of a flagpole, we're looking at the shadow of somebody that's 6 foot tall. So you're trying to figure out how tall that that tree is based on that. So, doesn't look like there's much trouble there. Number 22, they have the screen resolution, but they have the pictures there. So you've got 1680 over 1920 equals 1050 over x. Got the length of an instrument. They're comparing the body length and the total length, the body length being 15, the total length being 24. So you're comparing some things there, but not much difficulty there. I think you can probably go through here and do those without much problem at all. So I'll let you do that for 6.5, and we're ready for chapter 7.